Walk onto a modern manufacturing floor, and you see thousands of robotic arms moving in an unbroken, highly synchronized rhythm. Every weld, sort, and assembly happens exactly on schedule. But beneath this motion is a massive operational bottleneck. When these machines need to learn a new movement, that rhythm has to stop completely. Decades ago, teaching a robot meant a human operator had to physically puppet a controller, guiding the machine through every point of its soldering path. As production scaled up, this manual puppetry was replaced by engineers typing code on a terminal. But they still had to run that new code on the actual hardware, watch the robot move, measure where it failed, and rewrite instructions. On a dense assembly line with entire floors of hardware packed tightly together, testing required shutting down the real-world operation entirely. Freezing a line for hours to test new software means sacrificing millions in scheduled output. It also means burning through raw materials during physical trial runs and risking catastrophic damage to the robots themselves if the code contains a collision error. Consumer demands now shift rapidly, requiring continuous updates to product lines. A factory cannot survive if it must paralyze its physical operations every single time a machine needs to learn a new task. Global supply chains demand agility. While physical steel and concrete are inherently rigid, orders for new automotive models, custom electronics, and seasonal logistics can change overnight. This creates a direct conflict. Manufacturers have to continuously design and refine highly complex robotic movements, but they cannot afford to pull the physical assembly line offline to do it. The way out of this bottleneck isn't building a more durable physical robot. It is constructing a parallel space where errors have zero physical consequences, allowing testing to happen without ever touching the actual machines. A digital twin is a living, mathematical replica of the production floor, running the exact same logic and spatial coordinates as the real world. To access this replica, engineers use a software platform called RoboDK. It acts as the bridge, providing an environment for offline programming where users can build and refine robotic operations completely separated from the active factory floor. This animated split-screen logic graph illustrates the dual workflow. On the right, the physical factory continues outputting today's product without interruption. Simultaneously, on the left, engineers inside RoboDK design and test movements required for tomorrow's product. In the digital space, engineers can freely push the limits. They can deliberately crash the robotic arm into a barrier, twist its joints to extreme angles, and reset the simulation instantly to optimize the path. When the perfect route is established, that verified data is sent straight to the active factory. By isolating the trial and error process entirely within RoboDK's offline environment, factories strip the physical cost of failure down to zero. But a digital sandbox is useless if it behaves like a video game. For offline programming to work on a real machine, the virtual environment must perfectly obey the strict laws of physical reality, including exact gravity, surface friction, and the momentum of heavy payloads. To achieve this accuracy, RoboDK integrates NVIDIA Isaac Sim. This simulation engine injects hyper-realistic physics directly into the digital twin, ensuring that if a part falls in the simulation, it falls at the exact same speed and trajectory it would in the physical world. When the digital twin mathematically mirrors physical reality, it becomes an ideal training ground for artificial intelligence. This generated video shows how AI leverages that environment. Instead of a human manually typing in coordinate after coordinate, machine learning algorithms take over. The AI is running thousands of slightly different picking trajectories in a fraction of a second, discovering micro-efficiencies in the angles that a human engineer could never calculate manually. The integration of NVIDIA Isaac Sim and machine learning transforms RoboDK into an active engine that independently learns, adapts, and invents robotic solutions. The true test arrives when the virtual process ends. The AI-generated, perfectly optimized code is extracted from RoboDK, carried down to the physical factory floor, and uploaded directly into the waiting robotic hardware. Because all the errors were burned off in the simulation, the physical machine executes its new task exactly right on the very first try. Massive, heavy-duty automotive robots instantly begin to weld strong, flawless joints without requiring a single physical test run. This accuracy transfers directly to other sectors. Warehouse robots seamlessly sort packages at lightning speeds the moment they are turned on. and automated inspection systems immediately begin repeatable, high-precision quality checks. Knowing a robot's exact predetermined path down to the millimeter is also what makes collaborative robots, or cobots, possible. Because their movements are perfectly mapped offline, they operate safely just inches away from human workers without needing heavy safety cages. In this workflow, the mechanical arm on the factory floor acts as a 3D printer for digital thought, executing movements already perfected in simulation. As AI and digital twins handle the complex mathematics of motion, the human workforce is shifting. Technicians and operators are moving away from manual physical intervention and reskilling to become digital architects, managing the simulations that govern the machines. Adopting AI tools and digital twin logic allows this workforce to create highly sustainable, waste-free operations. By optimizing every millimeter of movement and every ounce of material digitally, factories can significantly reduce their physical energy footprint. The industrial logic of pouring concrete, bolting down steel, and hoping the assembly line works is obsolete. The smartest, most efficient physical realities of tomorrow are now entirely built, aggressively broken, and permanently perfected in a virtual world long before a single switch is flipped in reality.